So the last section was a lot of information delivered rather quickly. And so in this section and the next, we're gonna take a bit of a step back and actually work through some examples to help you understand all of the different concepts that I just explained. So our first example is going to be about proofs of the form of these three lemmas here. Right. So in each of these cases, they're actually like the premises are always the same, and the point is this H hypothesis is always a complex conjunction, and of course these examples are a bit artificial, but you could definitely find things like this in practice just because you have some complex type definitions and they happen to expand into a conjunction like this. And the point is, so we always want to conclude that one of these conjuncts is true. So here, for example, the A, and here we want to extract the B, and here we want to extract the B and C. And in the first case, it's not so bad, right? It's just a single call to lm left. But already in the second example, we have to do first lm right in order to get into this part, and then lm left in order to get into this part, and then lm left in order to get the actual B. And you know, this is the sort of thing that a theorem prover should help us with, that we don't want to do manually. So we're gonna write a tactic for it. And yeah, I'm just gonna walk you through the actual definition of the tactic without further ado. So here's the kind of entry point of our tactic. We're gonna call it destruct and it takes a name, specifically the name of a hypothesis that we want to destruct, and the hypothesis is going to be a conjunction, usually. And this is going to be a tactic unit, right, because we don't expect this tactic to give any useful result. And what we're going to do is, so first we use tactic.getLocal, which we've seen before. This gives us the expression corresponding to the name of this hypothesis. And so this expression is going to have the form expr.localconst and then a bunch of thing inside the local const. And this represents the hypothesis that we're going to be working on. And then when we have that, we're going to call destruct and helper with this expression. Okay, and now we define destruct and helper. And the first thing we do here is we infer the type of a hypothesis. So this is generally how you get the type of a hypothesis, right? If you have a hypothesis H of type N, then infer type with H will give you back the N. And in this case, we expect this type to be a conjunction, usually, because otherwise our tactic is kind of pointless. So we match on the type, and we say, well, if it is a conjunction, then we can extract the left conjunct and the right conjunct and call them A and B. Right, so here we're using the pattern matching feature with a quotation here and then an anti-quotation of both A and B. And so in this block here, A and B are in scope and are expressions which are respectively, you know, the left-hand side and the right-hand side of this conjunct. Okay, and then we're gonna try a few things. So the first thing we're gonna try is, okay, maybe H is already what we were looking for, right? So for example here, our actual goal is a conjunct, and if that's the case, then we want to maybe match a conjunct but not actually process it any further because it might already solve the goal. So that's what we try first. If this fails, then we go to the next block down here, where we do the following. So we take the left conjunct, and this is going to be a proof of A right here, because like if you look here, it's essentially what we do up here in order to eliminate a conjunction. right, we use and.lmleft and and.lmright. So if h has the type a and b, which we've made sure because we pattern matched on that, then end.lmleft of h is going to have the type a. And we use a little trick here involving pre-expressions, right? So recall that with the two backticks here, we construct a pre-expression, and then we use tactic.toExper, which is a bit unfortunately named. It should be named elaborate because it does elaboration, which means that it turns a pre-expression, so this guy here, into a fully elaborated expression. And just to remind you, what that means is it's going to fill out all the implicit arguments and instance arguments and everything that's going on there. Why do we do that? Well, because if we wanted to give, so if you look at end.lmleft here, it takes two implicit arguments and then the hypothesis that we're eliminating. And if we were to construct a fully elaborated expression ourselves, then we would have to give this a and b explicitly. And when we do it like this, we can do what we usually do when we write lean, which is leave the a and b implicit and let lean figure them out. And this is going to work like exactly the same. It's just less work for us. And of course we could also like restructure the whole thing in order to avoid this. But you know, why would we? Okay, and then so this HA is now a proof of A, and then we continue with this proof of A and you know recurse into it. And of course A might again be a conjunction. This is why we do the recursion. So for example here, when we destruct this conjunction, we get a left-hand side of A, but then a right-hand side of B and C and D, which is again a conjunction, and so then we recurse into that. Okay, and then the last block here, so if this also fails, then we go into the last block, and this last block essentially does exactly the same, only with the right-hand side, right? So here we did lm left, here we do lm right, and so we get a proof of B, and then we recurse into that. Okay, and then of course we still have the question, okay, if our original hypothesis did not actually have type A and B, for some A and some B, what do? Well, we try to solve the goal with this thing exactly, and you know, if it fails, it fails. Okay, so let's try this out on a few examples. So here we have a lemma where we have A and B and C, and we want to derive A, and as you can see here, our destruct and tactic just does it for us. And note that we have to give a backtick H here because this is a name that we're giving to destruct and, right, like here. If you call tactics within a begin and end block, then they do this conversion for you in some magic way that we're not going to go into here. But if we use just normal tactic, then we have to remember that a name needs to be written with a backtick. Okay, so here same thing, but now we extract the B, also works. Same thing, here we extract the B and C. This also works, right, because this conjunction is really written like this. And so, you know, it goes into the left-hand side first. That doesn't work, but then it goes into the right-hand side and it tries to solve the goal with this immediately. And, you know, that happens to work in this case. And here's an unfortunate case that doesn't work, right? Deriving A and C does not work. And this is kind of down to the implementation of our tactic, right? If this were B and A and C, then this would also work. but it is really A and B and C. So that's kind of unfortunate. You can probably think of ways to solve this problem. So for example, we could decompose the hypothesis H into a set of propositions that are proven, and then we could say, okay, here we want to prove, like we want to also prove a set of propositions, and then we see whether this set is a subset of this set. But of course, that's a bit more tricky, and so if you want to do some nice extra homework, you can try to do that. But for the moment, we have a tactic that handles a couple of obvious cases.